Welcome to Wavelet Synthesis, Part 2, and I'm Tom Irvine. And previously we went over synthesizing an acceleration time history that could be used for a shaker test or numerical simulation, such as a spring mass or FEA modal transient analysis, and also whereby that time history had to satisfy a shock response spectrum specification within some reasonable tolerance limits. Now, years ago, I worked on this NASA document called An Alternative Method of Specifying Shock Test Criteria, and my co-authors were Robin Farabee, Joe Clayton, and Dave Aldridge, and then myself, Tom Irvine. I'm the one that actually came up with the numerical method to make the contribution for this document that we're going to go over today. And the purpose is to synthesize a time history to satisfy a shock response spectrum where the resulting time history resembles the measured time history. Now, the motivation for this was that the space shuttle program had two solid rocket boosters that were recovered and refurbished in between flights, and obviously we've flown. And as each of those boosters was, after being ejected and was descending, then 3 parachutes were deployed, but even with the parachutes deployed, then that booster had a pretty significant water impact shock event. And of course, depending on winds and wave heights and all sorts of other variables. And there was a avionics box called the IEA avionics box, fairly large inside the solid rocket booster that needed to be recovered and refurbished and reflown in between flights. And the idea was to come up with a shock level for that IEA, integrated electronic assembly, that did satisfy a shock response spectrum based on water impact, but whereby also the time history would resemble an actual impact event, not just some arbitrary time history. So as a review, a given time history has a unique SRS. On the other hand, a given SRS may be satisfied by a variety of base inputs within prescribed tolerance bands. We went over that last time we met. So the SRS format thus offers flexibility, and a common shaker shock testing approach is to use a burst of wavelets such that the synthesized time history resembles a transient sine sweep with descending frequency. Well, that is a very elegant way to satisfy a shock response spectrum, but that sine sweep is not going to represent a true time history in terms of what we would measure with an accelerometer out in the field. So yes, the drawback is that the time history used to satisfy the SRS may be very dissimilar from the measured source data. Brings up a whole set of concerns. What if our system, our physical system or our analytical system is nonlinear, for example? What about multi-mode response? What about the phasing between the responses in terms of the modal response and then natural frequencies and so forth? Now, some of these concerns can be quantified in terms of the scalar temporal moments, which quantify the energy, and we've talked about the Arias intensity, the RMS, skewness, and kurtosis. Well, those are some ideas set forth by numerous authors, including Dave Smallwood and Jerome Kapp and others as well. And those ideas of using these additional parameters in the middle have just not gained traction in industry. Well, I wish they would. I wish industry would embrace those other parameters as well to better characterize and hopefully get the true damage potential of these shocks, because as we found out last time, that SRS simply, well, it's not good enough. So these concerns have led to a desire to synthesize a time history which resembles the real-world event while still satisfying the shock response spectrum specification. So we are going to take a measured reference time history and use it as a basis for synthesizing a time history to meet the shock response spectrum specification. So there will be trial and error. This will be a Rube Goldberg-like process. So hat tip to Rube Goldberg, one of our patron saints. So random number, trial and error, generation, built-in convergence. It is in the vibration data GUI package, which we're about to run. So the first step is easier done than said. We're going to decompose the reference time history into a series of wavelets. And it's going to be random number generation with convergence. There's no Fourier-like transform. It's surprisingly easy and surprisingly accurate. An acceleration wavelet, as you recall, has zero net velocity and zero net displacement. A series of wavelets likewise has these same properties. Saw that last time. Wavelets are very amenable or efficient or user-friendly for shaker shock testing and are also very convenient for analysis as well. And we'll do an example here, and we're going to use hundreds of wavelets to model a reference time history. And then the next step, so what we want to do, the big picture here is we want to take that measured time history, model those wavelets, and bend and stretch those wavelet amplitudes, then to satisfy a given shock response spectrum specification. So the second step is to randomly vary the wavelet amplitudes so that the modified wavelet series will have an SRS that matches the specification as closely as possible. The number of iterations may be 16,000 or so. We'll probably use a different number though. The modified time history will thus have some distortion relative to the reference time history, but this is needed to shape the time history so that shock response spectrum then meets the new specification. The second step yields a shock response spectrum that has some peaks and dips relative to the specification. This is a consequence of trying to adapt or bend and stretch a measured time history to fit a smooth SRS, but we can deal with that. So the third step is to add wavelets, add in extra wavelets, so that the resulting SRS meets the specification within, say, plus and minus 3 dB tolerance limits. Well, let's try and do better than that. Let's see if we can get within plus and minus 1 dB tolerance bands, or tolerance limits. So the third step, adding these additional wavelets, then that's going to cause some extra distortion that we're going to accept. And the amount of distortion depends largely on how much the SRS specification differs from that of the reference data. That's reference data being our source accelerometer time history. So let's go to the MATLAB GUI package. And as I make this, that GUI package is up to 13.1, but we have 12.4 newer today. You're good to go. So we are going to then go to import data, to library, to seismic, to time history, a little bit of zigzag in there. And let's use the El Centro North-South as our model today. That's our reference data. So we want to take El Centro and convert it to a series of wavelets and then modify those wavelets to satisfy a certain shock response spectrum, which is going to be on the next slide, or 2 slides. So there's the accelerometer time history from El Centro, that's the north-south, and acceleration G versus time in seconds, gain up to a peak of about 0.35 Gs, and very famous time history, strong motion data, and even though this was from 1940, it is still used today for different simulations and so forth. So next we're going to call in our specification for today. It will also be a familiar one. We go to import data, to library, to seismic, to SRS, and Vandenberg Air Force Base, 1% damping. And here we are, once again, we've got acceleration G, actually peak acceleration versus natural frequency and heights. And it's 1% damping. And it's got a peak amplitude, or peak G level, at the highest net case of about 0.9 Gs or so. So launch vehicles at Vandenberg need to be designed and analyzed to this level, but not tested because they're too big. And there's also the ground support equipment as well. So we're using this as a sample level, but of course you can substitute in your own shock response spectra, whatever you might have. So next we're going to go to then signal analysis. We'll go to shock response spectrum and down to acceleration. Let's go over to earthquake synthesis. Now even though this says earthquake, we could use it for other types of shocks as well, like automotive crash hazard, for example. And even though there's a separate pyroshock synthesis, we could also use the earthquake synthesis for pyrotechnic shock synthesis as well. So whatever shock you might have that's characterized by a response spectrum, and you have some representative time history, you can use earthquake synthesis. Okay, we go to the earthquake synthesis. The script synthesizes a time history using wavelets to meet an SRS where the resulting time history is modeled using measured data. We'll enter SRS and time history, and then our SRS specification that's the Vandenberg 1P, P means percent. So just highlight that or click on it. Now our reference time history over on this other tab, of course, is going to be L central north-south. Make sure that is highlighted. Okay, now we're to the part where we set up the calculation. And there's a reminder, these top left edit boxes are read-only, just to remind us that we have Vandenberg 1% and L central north-south. Now that VAFB stands for Vandenberg Air Force Base, but it's recently been renamed to something like Vandenberg Space Force Base or something like that. We'll do English units. Now we're going to be fairly aggressive and look for an error limit in our SRS of 1 dB. So we're going to take the SRS of the synthesized time history and we're going to modify it until hopefully we can get within 1 dB. Our sample rate will be 10 times higher than the maximum SRS frequency, so that would be, we've got 20 hertz is our highest SRS frequency, so 200 hertz sample rate. The number of iterations, now this is a several part process, and I need to go back and do a little neat and tidy organization here, but we'll do what's called 80,000 iterations. That's actually for the second step. We can specify a displacement limit, which we will. It will be plus and minus 5 inches. The duration of our synthesis will be 54 seconds, which is the same as L central, but doesn't have to be. The primary wavelet, so we're going to take L central and we're going to transform it into 800 wavelets. Again, easier done than said. Our Q value is 50, which is equivalent to 1%. And then we're going to take that, and then we'll do the 80,000 iterations, just trying to adjust the amplitudes of the wavelet components to get a better agreement in terms of the SRS of the synthesis with the SRS specification. And as needed, we'll add up to 100 additional wavelets just to fill in gaps and so forth. And calculate. It'll take you a couple minutes, but we'll just go ahead and advance the slides. So you'll see a series of plots along the way, and then here is the final set of acceleration time histories. These three are all acceleration in g versus time in seconds. And the top you've certainly seen before, that's the L central measured data, acceleration in g versus time in seconds. The middle is the result of decomposing L central into 800 wavelets, and that replication is very good. It's not perfect, and it's not intended to be perfect, but it's a very good representation. Now the bottom is the modified acceleration. So we went then and took the wavelet decomposition and we just tried rescaling wavelet amplitudes. We've added in up to 100 extra wavelets, and we come up with a new waveform. Now the new waveform then departs somewhat from the L central, but that's inevitable because we are modifying the decomposition so that the resulting SRS matches the Vandenberg SRS. If somehow then the L central matched the Vandenberg SRS from the beginning, this would not be necessary, but of course it did not and does not. So that's why we had to go through this decomposition and scaling. Now, to what extent does that modified look like an actual earthquake? I think this reasonably does. There's no quantitative metric that I have to offer, but just kind of the eyeball check and so forth, I think that modified is plausible for an earthquake. And one thing you'll also notice is that the peak amplitude is less, and that's because the peak of the Vandenberg SRS is lower than the the peak of the SRS of the raw measured data. So we had to downscale the amplitude, but we also had to do some frequency-dependent manipulations and add some wavelets. So I think we did a good job. Perfect? No, we're not. This is not about perfection. Nothing is exact in this course. Okay, I think we covered that there pretty good. So I'll just read this anyways. The bottom time history has additional wavelets to improve the SRS match and scaled downward since the El Centro SRS plateau is greater than the specifications plateau. Okay, let's check. Now that top acceleration time history you just saw, because that's the modified acceleration g versus time in seconds. And once again, I'm going to say it kind of sort of reasonably looks like an earthquake. Let's go and integrate it to velocity in inches per second, and then we find that we get a fairly good looking velocity time history. It's stable, begins and ends at 0. Could it be a little more symmetric and pleasing to the eye? Yes, but we'll take what we can get there. And then the displacement in inches versus time in seconds, it's within the plus and minus 5 inches that we specified, beginning and ending at 0. So you could use this then, maybe for a shaker table test, as long as your control computer can do what's called time waveform replication, TWR, or you could use this in an analytical model, spring mass or multi-degree of freedom, to base drive your model. You could do that. Do a modal transient, modal superposition analysis. Okay, now here is the resulting SRS. We've got shock response spectrum, Q is equal to 50. Along the y-axis is acceleration g. Along the x-axis is natural frequency in hertz. Now the middle line is the Vandenberg, which you've already seen, the Vandenberg SRS. And then we've got a yellow and green line. Probably should change colors, make them more distinct, but those are the plus and minus 3 dB tolerance bands. Again, that kind of greenish color and yellowish color. And then we have our synthesis is the blue curve, and for the positive, and the red curve is the synthesis for a negative. Now those values for those SRS of the synthesized did come within plus and minus 1 dB of the nominal level, which is doing pretty good there. We did a very good job, and we could go on then and use that time history, as I mentioned, for a finite element model or even spring mass models. I think we could do that. So let's see what else we have here. So the method is thus successful in generating an El Centro-like time history to meet the specification. Well, one more slide to go, and we're going to go back and revisit some things we did last time, but also take a look at what we just did. So here's a table. These are the peak values and temporal moments. So the last time we met, we used 3 different waveforms. Then to satisfy that Vandenberg specification, we tried a reverse sine sweep, a random, and an exponential decay. Turns out they all had the same peak accelerations, a little bit different in velocity. Reverse sine sweep, the least velocity of those 3. Reverse sine sweep also having the least displacement of those 3. Now we notice that the energy content was different. So the reverse sine sweep would have 0.016 g squared second, and then the worst case was the random at 0.04 g squared per second. Now each of those 3 satisfied the specification within about plus and minus 1 dB tolerance, but yet their energy levels differ by a notable amount. So as we mentioned last time, that maybe our component in the test situation or analytically would then pass the reverse sine sweep but fail the random if it were sensitive to the energy parameter. So that's something to think about. Well, how does El Centro fit in? Well, we like El Centro, the modified El Centro, because it's realistic. It does have a higher peak acceleration, G level. It does have a peak velocity that is substantially higher. Its peak displacement is definitely higher. And its energy actually comes just a ways within the random. Now, reverse sine sweep and random and exponential decay were also highly optimized to not only give a good result in terms of accuracy, but also to minimize peak acceleration, peak velocity, and peak displacement we were not trying to do any optimization of El Centro as we modified it. We were just letting the chips fall where they may on that, although we did control the peak displacement to within plus or minus 5 inches. So which of these should you use? Well, for realism, I would highly recommend using modified El Centro. You can always do like different sorts of Monte Carlo analyses for as well, and generate a whole family of synthesized time histories and so forth if you want to go that route. And again, I've said it before once today and once or twice last time, but I really, really wish that industry would adopt additional parameters for SRS specification. It could be the Arias intensity. It could be one of the Smallwood temporal moment parameters as well, but we definitely need a better accurate, more realistic way to characterize the damage potential shock than the current SRS alone. Yeah, keep using the SRS, that's fine, that's good, but yeah, you hear what I'm trying to say. We need further control, but hopefully someday industry will come around to that, even though that idea has been kicking around since actually the 1950s. So the reverse sine sweep synthesis had less energy and this may cause an undertest, even though its SRS matches the specification. It's a restatement of what I already said. So I hope you enjoy this tool and you can make use of this in your own way. And thanks for coming. You have a great rest of the day and week, so forth. And see you again soon. Bye for now.